Absolutely. I'll keep the Spider-Man hook, the science, the strength versus toughness explanation, the spider farming problem, genetically engineered silkworms, and the final swing test, while making it much shorter and more engaging for YouTube. Could real spider silk actually let you swing like Spider-Man? It sounds impossible. But spider silk is one of the most incredible natural materials on Earth. In Spider-Man 2, Peter Parker stops a runaway train using his webs. Obviously, that's fiction. But real spider silk is surprisingly powerful. Some types of spider silk can be stronger than steel by weight, and certain varieties can be dramatically tougher than Kevlar. So I wanted to find out just how impressive this material really is. At the Blackledge Spider Lab at the University of Akron, researchers showed me something I didn't know. Spiders don't make just one type of silk. They can produce several different types. Some silk anchors the web. Another creates the spiral. Some is sticky enough to trap prey. And another type wraps the prey. But the strongest structural silk is called dragline silk, also known as major ampullate silk. This is the material that holds much of the web together. To test it, researchers extract the silk from a spider and place a single strand into a machine that slowly pulls it apart. As the machine pulls, two things happen. The silk experiences stress, meaning the force acting on its tiny cross-sectional area. And it experiences strain, meaning how much it stretches. Eventually, the silk breaks. One sample reached around 600 megapascals of tensile strength. To put that into perspective, a rope of spider silk with a cross-sectional area of about 1 square centimeter could theoretically support an enormous amount of force. But there's an important detail. Steel can actually have a higher ultimate tensile strength. So why is spider silk considered so impressive? Because weight matters. Steel is much denser than spider silk. For ropes with the same length and mass, spider silk can have a much larger cross-sectional area. That gives spider silk an incredible strength-to-weight ratio. And strength isn't the only thing that matters. Imagine a rock climber falling. A rope doesn't just need to be strong enough to hold the climber. It also needs to absorb the energy of the fall. That's where toughness becomes important. Spider silk can stretch dramatically before breaking. One sample stretched to about 70% of its original length. That stretching allows the silk to absorb a huge amount of energy. And this is exactly what a spider needs. When an insect crashes into a web, the web can't behave like a brick wall. If it stopped the insect instantly, the insect could simply bounce away. Instead, the silk stretches and gradually slows the insect down. That's one reason spider silk can be so tough. Some spider silk, particularly from the Darwin's bark spider, has been measured at extremely high toughness levels. But there's a problem. If spider silk is so incredible, why aren't we making everything from it? Because getting enough of it is incredibly difficult. Spiders are difficult to farm because they're territorial and cannibalistic. And even collecting silk directly from spiders is extremely labor-intensive. Natural spider silk can therefore become extraordinarily expensive. So scientists asked a different question. What if we could make another animal produce spider silk? One of the most interesting attempts involves silkworms. Humans have been farming silkworms for thousands of years because they already know how to produce large amounts of silk. Scientists began combining silkworm genetics with spider silk genes. The result? Transgenic silkworms. These silkworms can produce silk containing spider silk proteins. Scientists can introduce spider silk genes into silkworm DNA using genetic engineering techniques. One approach uses a system called piggyback, which works like a genetic cut and paste mechanism. More precise techniques, including CRISPR-Cas9, are also being explored to insert spider silk genes into specific locations. And this could be a huge breakthrough. Instead of trying to farm millions of spiders, we could potentially use organisms that are already easy to raise and produce silk at scale. Companies and researchers are already exploring synthetic and genetically engineered spider silk for applications ranging from clothing and protective materials to medical technology. But can it actually do what Spider-Man's web does? Can you swing from it? That's exactly what the researchers wanted to test. A strand of transgenic spider silk was prepared and tested in a climbing gym. One continuous strand was strong enough to support a person's weight. Then came the real test. Could someone actually swing from it? 3, 2, 1. The silk held. It was strong enough to support the person and allow a swing. But there was another problem. Spider silk is incredibly thin. And when it carries a lot of force, that thin strand can become extremely uncomfortable and even cut into your skin. So no, we're probably not getting Spider-Man-style web swinging anytime soon. But the science behind spider silk is still incredible. It's strong. It's lightweight. It's extremely tough. And it can stretch while absorbing enormous amounts of energy. The real challenge isn't proving that spider silk is amazing. We already know that. The challenge is figuring out how to produce it cheaply, consistently, and at massive scale. If scientists can solve that problem, spider silk could eventually become much more than something found in a spider's web. It could become a material used in advanced clothing, protective equipment, medical technology, and possibly applications we haven't even imagined yet. So the next time you see a tiny spider web in the corner of your house, remember, you're looking at one of nature's most remarkable materials. And who knows? Maybe one day, Spider-Man's web won't be science fiction anymore.